Okay, so today is kind of a wrap-up of all the SN1, SN2, E1, E2. Trying to remember, did we do tertiary butoxide at the end of class? The very end of class on Friday? Okay. Okay. I've released chapter 12 because the first part of that will be for Wednesday. But what questions do you have about the SN1, SN2, E1, E2? You can ask them. You can put them on. You can type them in on Piazza. I've got that window opened if you don't want to ask publicly. Oh, that's right. We didn't do rings. We need to do rings. Okay. All right. So that's the last part of E2. So if I remember, when on Friday we talked about using basically a small, strong base, which the book's favorite is ethoxide, which will be problematic, but we'll ignore that for the moment. My favorite is NH2 minus because it's not. That is always going to, first of all, these are always going to do E2. Whenever you see those bases right now, they're always going to do, bless you, E2. That's what they're going to do. And so if they're going to do E2, which product are they going to form? Well, we have an issue. The first issue is that you need to identify the beta hydrogens that are anti-periplanar. Because if it's not anti-periplanar, these bases aren't going to remove those hydrogens. So that's the first thing you need to do, is find the anti-periplanar hydrogens. And then of those, you will form, if you have a choice, the most stable alkene. So the difference between E2 with a small base and E1 is that E1, any beta hydrogen you will lose. E2, it's only the hydrogens that are anti-periplanar. And where that comes into play is it comes into play with rings. Because sometimes I can make a ring that the beta hydrogen cannot be removed. Okay. Then if we have a sterically hindered strong base, in the sterically hindered strong base, what we have is something like tertiary butoxide. And in this case, again, we need to identify the beta hydrogens that are anti-periplanar. And then if we have more than one of those hydrogens that can be removed to give different products, what we're going to do is we're going to remove the least hindered beta hydrogen. Okay. So again, the difference between E1 and E2 is that E1, you'll always lose a beta hydrogen regardless of whether it is anti-periplanar or not. For E2, the first thing you have to do is find all the possible beta hydrogens that can be lost. And those are the hydrogens that are anti-periplanar. Once you find that, then it's the choice of, well, if there is a choice, most stable for small versus removing the hydrogen that is the least hindered if it's tertiary butoxide. Okay. And so we did the acyclic systems where you had to rotate the rotate the sawhorse projection to get the groups anti-periplanar to each other. Now we need to make that go into rings. So the first thing that we need to look at with a ring is that if I have, for instance, a leaving group like a chloride, and I have two hydrogens that are beta, HA and HB, let's say. And again, first step is always, what's the alpha carbon, what's the beta carbon, does the beta carbon have beta hydrogens? So in this case, I have two beta hydrogens, HA and HB. And the question is, which one of those two can be removed by a strong base in an E2 mechanism? Okay. So if I'm going to do E2 on this, one of those hydrogens is going to be anti-periplanar, and one of them will not be. So if I change this flat cyclohexane into a chair, we can kind of make that clear. So here's my two carbons. If this is the alpha carbon and this is the beta carbon, where's the chlorine? Where should the chlorine go on the alpha carbon? Should the chlorine go on to should it go on the equatorial or the axial position? If I'm looking at, and my perspective is looking down on the ring, where should the chlorine go here? Axial, and then the hydrogen would go equatorial. Okay. Why does the chlorine go in the axial position? Because that's the position that's above the plane of the ring. So then HA would be above the plane of the ring, and HB would be below the plane of the ring. So now if you're the base, the strong base coming in to do E2, which hydrogen can you remove? And your choices are A, HA, HB, both, or I suppose neither. So, which one is it going to be? HA, HB, C will be both, and D would be neither. I'm going to be honest, neither's going to be pretty boring. All right, we have 18 B's and 4 A's and 1 both. It's not both. So if I'm talking about anti-periplanar, I need to have the hydrogen that is going to be anti-periplanar to the chlorine, which is going to be HB. So you can see in the way I've highlighted it, and if you were to look down this position, the Cl and HB would be anti. So HB is the only one that can be removed.
For an E1 reaction, does it matter since it's 2 steps?
No. In an E1 mechanism, what will happen is once in my chair, once I end up losing the chlorine, the chair is going to kind of do this, where it's going to become a carbocation. And in that case, either of the hydrogens would be able to orient themselves parallel to one of the empty orbitals. So in an E1, you could lose either HA or HB would be lost. And the reality is actually probably 50% of HA, 50% HB.
But you'll get the same price either way, right?
Yes, yes, yes. And so in this case only HB is going to be removed. Okay, because it's the only one that's anti. I can twist this ring as much as I want, but I am never going to make HA anti-periplanar to chlorine. The ring doesn't twist that much. Right? Does everybody see that? So then the question is, what's the relationship between Cl and Hb? Are they cis or are they trans? Between chlorine and Hb, cis or trans? Trans. Okay, so Cl and Hb are trans. So what does this mean? This means that when you have a ring and you have a specific geometry of the leaving group, in other words, the leaving group's got to be on a boulder-dashed wedge, you will only be able to deprotonate in an E2 the hydrogen that is trans, the beta hydrogen that is trans to the chlorine. That's what that means. Because that's the only one that can be oriented anti-periplanar. Okay. So what does that mean in terms of a problem? What it means in terms of a problem is, if I said, for instance, I gave you this molecule and I said, let's do this by E2. And I write my products. In other words, I'm going to lose a beta hydrogen. I'm going to write my possible products. So I'm going to lose a beta hydrogen and the chlorine, because that's what's going to happen. I can either end up with the double bond on the top, or I could end up with the double bond to the ethyl group, or I could end up with both products, or I could end up with neither. So, I'll give you a minute. Notice I haven't given you a base. I'm just asking about what are the possible products of this reaction. A, B, both of them, or neither of them. So which one is the major, which ones are the possible products? We'll get the major here in a minute. Okay, we ready to vote? So possible products. A, B, both, or neither. Okay, we've got 2 A's, 16 B's, and 5 boths, and no neithers. Okay. So I have to look for my beta hydrogen that is trans. So first of all, I need to identify alpha, beta, beta. What's the beta hydrogen up here? Bold or dashed? So I might have to put the hydrogens in if they're not there. And down here it would be dashed. So which of the hydrogens can be removed? The dashed one, the one that's trans. So this is the only one that could be removed. This one cannot be removed in an E2. Okay. So just the bottom one, so that means that B is the only possible product for this reaction. Okay. And in this case, the major product would be B, regardless of whether I used NH2 minus or tertiary butoxide. The only possible product is B, and so there's no choice. I have no choice as to which one to choose. Okay. So when we're writing the products, we have to identify alpha, beta, and then we have to, if we're identifying all the possible products, and that would include E1, we'd find our beta hydrogens and we would lose them. But when we're doing E2, we need to say, okay, I can only lose the beta hydrogens that are trans. And if that only leaves one product, then it doesn't matter what the base is. If I have more than one product, then I'm going to have to apply my rules for the bases. Okay. So in terms of possible products for E2, it's only B. What are the possible products if this was E1? If I said, okay, let me change this mechanism now to E1. If I change this to E1, what are my possible products? There's no restriction now on stereochemistry. So if I change this to E1, my major products are both. So they're both possible products. Which one would be the major product? Let's vote on that. So if I change this to E1, what is the major product? A, B, both, neither. So if I change this to E1, what is the major product of the reaction? A, B, both of them, or neither of them? If it's E1. Maddie. Up there. Oh, multiple Maddies. I just have to be able to see it. Okay. All right. Let's see. We've got 18 boths. And we've got 3 A's and 6 B's. So if I go to E1, what's the rule for the major product in E1? E1, the major alkene product is always going to be the most substituted, most stable. For E1, that is always the rule. So in this case, A or B, which one is more stable? They're equally stable. Because how many alkyl groups do they have attached to the double bond? 3. So again, if you're unsure about that, just put in the hydrogen. There are 3 alkyl groups attached to each double bond, therefore it is tied. Therefore, they are both more substituted. Okay. Now, I can make there, let's see. So there was a problem set that you may or may not have done that's been kind of floating from folder to folder. I kind of keep moving it down a folder. That's some series of multiple choice questions that look like this. So these kinds of problems. I can make subtle changes to this, and it's a whole new problem. So for instance, I could say and if I'm writing this as a multiple choice problem that may or may not have more than one answer, all I'm going to do is I'm just going to simply write the double bond to each of the beta carbons, regardless of whether it has a hydrogen attached to it or not, because if it doesn't have a hydrogen attached to it, it's not going to ever be an answer, but it's a multiple choice answer. So in this case, I only see 2 possible products, A and B. C again is going to be both. D is going to be neither. Okay. So here are going to be my questions, because I can ask multiple questions from this problem. Number 1, E1. What would be the major product or products of E1? Number 2, with NH2 minus, which is a small, strong base, what would be the major product or products of that reaction? Number 3, tertiary butoxide. What would be the major product or products of that reaction? Okay. So, I'll give you a couple minutes. Go ahead and think about those 3 scenarios, and we'll vote on them one by one. What would be the major product of each one of those reactions? that's there. It's that, right?
Yes.
Was the first thing you wrote today. So if you're forgetting what the bases are, that was slide number 1.
Yeah, then add that so as well. Are we close to are we close with answers to all 3? Or questions about any of those? We'll vote first. Okay, let's go ahead and we'll vote on them one at a time. So, for number 1, if we do an E1 mechanism, what's our major product? A, B, both, or neither? A, B, C, or D? Okay, E1. Right. E1, the major answer is C. Okay? Next, NH2 minus. If I change the base to NH2 minus, what is the major product? A, B, C, or D? Okay. All right, the major answer there is C. All right, so for tertiary butoxide, what would be the major product of the reaction? A, B, C, or D? major answer is C with 17, followed by A with 8, and 2 B's. Okay. All right, so these problems, again, I'm kind of beating something dead here, whatever animal you want. First thing, A, you got to find alpha and beta carbons and hydrogens. Then secondly, depends on the mechanism in terms of what you can lose. So for E1, once I find my beta hydrogens, it doesn't matter what their geometry is, because they both can be lost either whether they're cis or trans. So then once I have my possible products, which I already have, A and B are possible products, which one is going to be the major one for E1? It's always going to be the one that's most substituted, which is, bless you, it's going to be A and B because they both have 3 alkyl groups attached to the double bond. So C is the major product there. Now NH2 minus for this one. They call this HA and this HB because it gives products A and B. Which of those hydrogens can be removed by the NH2 minus in an E2? Both of them can. So that means both A and B are possible products. NH2 minus always gives the most stable, most substituted. So in this case, I'm going to get both A and B because hydrogens A and B can both be removed in an E2 because they're trans. Okay? So now we're up to 3. So number 3, tertiary butoxide. Which hydrogens can be possibly removed from tertiary butoxide? Both A and B, right? So which one's going to be preferentially deprotonated? A or B or both? I'm not checking C yet. Which one would be preferentially removed? A? Why? So, is HA least sterically hindered than B? That's the proposal I hear. Now, first step is, what kinds of hydrogens are these? Primary, secondary, or tertiary? HA is a what kind of hydrogen? Tertiary. HB is tertiary as well. They're tied, but is there a difference in steric hindrance around them? One has a methyl group, one has an ethyl group. So which one would be more likely to be removed? The one with the least steric hindrance, which would be HA. So in this case, A would be the major product of the reaction if we go to looking at the steric hindrance around those 2 beta hydrogens. So it'd be easier for the tertiary butoxide to get at a methyl group than it would be to get at the ethyl group. Yes. So again, these two, whenever you see tertiary butoxide or NH2 minus, or in the textbook, the alkoxides, those always go by E2. Always. And that's primary, secondary, or tertiary halides. They all go by E2. So it's assumed that those strong bases go by E2. And these bases are built to only do elimination. They're built so that they don't undergo substitution. So whenever you see them, it's always going to be an E2. Once it's an E2, automatically has to be anti-periplanar. The difference is tertiary butoxide will go for the less sterically hindered hydrogen preferentially. Does that kind of make sense? Does anybody have any questions?
So sterically hindered bases will always go for the less steric hindrance on the
beta hydrogen, yes. Because it's about trying to get at that, and the more sterically hindered it is, what it does is it raises the transition state up. Because for a 2 mechanism, so whenever you have a 2 mechanism, the major product is always based on activation energy, which means it's always based on the transition state energy. And that transition state energy is always based on hindrance. It's always based on steric hindrance. So trying to fit the tertiary butoxide to get HB is going to be a slightly higher transition state energy than it would be for HA. And that would cause that reaction to remove HA to go faster, and you would get the major product. On the other hand, a 1 mechanism always is based on the stability of the final product. And in that case, it must be that the activation energies are very, very, very similar. Although you could invoke Hammond's postulate for those kinds of reactions. It gets a little dicey here on how to completely go through the thermodynamics, but in this case, it's based on the stability of the products. Any questions about any of the SN1, SN2, E1, E2? You're going to see a lot of the same problems in chapter 11 that you saw in chapters 9 and 10. I think they just kind of they put the same problems in again to what it looks like. So it's important to keep track of all the features of SN1, SN2. Now we've thrown in E1. But E1, the key step is determine the alpha and the beta carbons. We do have rearrangements that are possible. So we have to keep that in mind. Okay. Any questions about any of those? So let me just... Let's say I gave you this reaction and I said, I would like to see all of the possible products that could be formed from this reaction. And then I have 2 choices, right? Now, because I have with rearrangement, without rearrangement. So first of all, tell me how I'm going to start this reaction. What's my first step? Protonate the OH. I'm going to protonate the OH. So when I protonate the OH, I'm going to end up with the oxonium ion. Going to end up with a oxonium ion that looks like a water molecule because what's going to happen next? That's not happening next. What's happening next?
Can there go an E1 or an E2, like, 'cause it's a small, strong base?
Well, before we get to E1 or E2, what's going to happen?
The water has to.
So the rules for this are going to be that if you form an oxonium ion and you have a secondary or tertiary system, you're going to lose the water. Okay. So I'm going to lose the water on this. So I'm going to lose water and I'm going to form my carbocation. Now, when I go through this carbocation intermediate, as I'm going to, what mechanisms are possible? I have a chloride, right? So that makes possible mechanism. If the chloride reacts with the carbocation, then I could get what mechanism? SN1. So it's possible that this could undergo SN1. So if this is SN1, then I could end up with the chloride here. Or what else could happen? Maybe the carbocation rearranges. So the carbocation could rearrange this way to form that tertiary carbocation. The first question I would ask is that legitimate? Is that legitimate rearrangement? Am I forming a more stable carbocation? Yes. So then what happens with that carbocation? It could undergo SN1, so I could end up with the chloride there. Is that the only possible carbocation rearrangement I could have? No. I could end up with this carbocation, that hydrogen shifting on that side, and what would I end up there? I would end up there with that carbocation. And what could happen there? I could do SN1 and I could end up now with the chloride there. And SN1 is always accompanied by E1. So each of those three carbocations could end up with alkenes. Right? So there's more alkene products that are formed here.
So what's my point here? That's a good question. What was my point? My point is I should probably go upstairs, and when I get upstairs, I should see whether I can order this compound. Because I'm not going to make it. Although I could, but I'm not going to. If it's available, I might order it, and I might run this reaction to see how many of those products really get formed, to see if carbocation rearrangements really occur in this case. It can be an awful lot of work. Because if I have how many different products and I want to separate them, that's going to be a column chromatography for like a week to try and get them all separated out, which I wouldn't do. I would put it into the gas chromatograph and see how many peaks I get. Of course, then again, I don't know what's what, so that's going to be a little bit of a problem. Maybe. But here's the thing. Even when we're doing alcohol reactions, we could end up with SN1, and will end up with SN1 if it's a tertiary or secondary system. But always what goes with alcohol reactions is SN1 and E1. So whenever we form an SN1, a carbocation, we're always going to get substitution and elimination. If I want to favor elimination out of this product, so in other words, I don't want any of the substitution products, what should I do? The way to favor elimination is to change the proton source to not HCl, but H2SO4. Use H2SO4 and heat. And then I'm going to eliminate the SN1 reactions and only get E1 reactions. Okay. Now, if I want to evaluate whether or not this thing can undergo carbocation rearrangements, that's easy enough to do. I just add H+. I use something like sulfuric acid and water, and I don't raise the heat. I protonate the OH, it forms a carbocation. Even if I form the other two carbocations, water comes in and adds, and I would end up moving the OH around the molecule. But one of the things that we have to remember is if we're going to do reactions with alcohols, you're always, if you end up with an SN1, you're always going to end up with E1 products as well. Okay? Right. So, if you have, for chapter 11, I've released that. I've released chapter 12. For chapter 11, it should be relatively straightforward. Well, maybe or maybe not, but it's all review of SN1, SN2, E1, and E2. So as you're reading through that chapter, if you already haven't, if you're reading through that chapter and you're going like, this is pretty boring because I've seen this before, great. If you're looking through that, it's like, I've never seen this stuff before, we have a problem. Okay. So we'll start chapter 12 on Wednesday, but if you have any questions about it, chapter 11, put them on Piazza, etc. I'm going to post the answer key when I get